Let's look at number 5 here. We're evaluating a definite integral, and again, we don't want to be plugging in the 0 in power 4 into this integrand. We got to figure out what the antiderivative is first before we work the bounds. So let's think about integral of sine of x or integral of sine of u. The rule is integral of sine of u becomes negative cosine of u plus c. So no need for u substitution. The antiderivative of sine x is just going to be negative cosine of x. Once we find the antiderivative, we can plug in our upper and lower bound. Power 4 gets plugged in for x first, minus, then we plug in 0 in for x. So negative cosine of power 4 is negative root 2 over 2, plus cosine of 0, which is plus 1. For number 6, limit as x approaches infinity. Now, if we're approaching infinity, we can compare degrees between numerator and denominator, and if the degrees match, then we simply take the ratio of the coefficients. So the highest degree we see is x cubed up here. That's a coefficient of 1. The highest degree below is is x cubed as well, and the coefficient is 4. So we take the ratio of the leading coefficients, 1 over 4, and that's our answer. Just be careful. Sometimes the problems may not have the degrees in descending order, so just make sure that you're picking out the highest degrees. They may not be the first term. Number 7, graph of f prime, the derivative of the function f is shown. Which of the following statement is true about f? Let's gather some information about the function f first. So if we're looking at f prime graph, we have to understand this is not the shape of the original function. Okay. So to help map this out, I like to indicate that the portion that sits above the x-axis represents where the original graph is going to have positive slope, and wherever f prime is below the x-axis, that indicates where the original graph has a negative slope. So we know, and also if it hits the x-axis, that's when the original graph has a slope of 0. So we know that up until 0, we have positive slope because all these points are sitting above the x-axis. So I create a sine line to indicate that. We hit a slope of 0 at 0, and then after 0, we experience negative slope. So the graph is going to rise until it hits 0, and then it's going to decrease. Okay. So let's look at our answer choices. Our function is decreasing from negative 1 to 1. We see that's not true. It increases to 0 and decreases after that. Increasing from negative 2 to 0, that is true, so that's our answer. Let's just go ahead and look at the other answer choices, though. Our function is increasing from 1 to 2. That's not true, since we can clearly see that after we've gathered information, the original function will be decreasing in that interval. There's a local minimum at x equals 0. We know that's not true. There's a relative max, increase followed by decrease. Function is not differentiable. Okay, so here's something I want to point out is that, yes, we do see some sharp turns here, but this is not the function. This is not the original function. This is f prime. So we can say that f prime is not differentiable because the slope of f prime doesn't exist everywhere. However, this is not the f function. This is the f prime, and the f of x is differentiable because every point has a slope that is defined. So even though it looks like the slope is not defined at negative 1, whatever this y value is, let's say this was 2, then f prime of negative 1 is equal to 2. That means the original graph has a slope that exists at negative 1, which is a slope of negative 2. So this is a little bit tricky here. F prime is the one that's not differentiable. F prime is not a smooth curve, but f of x, which we do not see in front of us, is a smooth curve. Okay, number 8. We have an expression here. Take the indefinite integral of x squared cosine of x cubed dx. This is not a problem that we can solve just by one rule alone, but if we see the parentheses, it's a good indication that this is going to be a u substitution problem, and if we can kind of see that this can work towards this specific rule that we have available to us, integral of cosine of u du, which is sine of u plus c. So if that is our target, if that's our goal, then we're going to identify our u value to be what's inside the parentheses, which is x cubed. So we'll let u equals x cubed. We find du dx, which is 3x squared. Cross product, we get 3x squared dx equals du. We solve for dx, we get du over 3x squared, and we make our substitutions. So the parentheses gets replaced with u, the dx gets replaced with du over 3x squared, and we see that our goal is to get everything in terms of u. The x squared does cancel out. There's a leftover of 1/3, which is okay. We push that out in front. But once we get past that coefficient, integral of cosine u matches with the rule that is available to us. So we apply that to be sine of u plus c, replace the u back in terms of x, and 1/3 sine x cubed plus c. All right, number 9, we have a function that is natural log of an expression. Find f prime of 0. Two-step process here. We need to first find f prime of x. We need to first find the derivative function, and then we can evaluate the slope at 0. So the rule that we're going to apply is natural log of u, which is u prime over u. Now within this expression, we're going to have to rely on the derivative for e to the u, which is e to the u times u prime. Okay, so first things first, we're going to apply the rule that applies to a larger portion of the problem first. So natural log of u, so this entire expression is my u value. So u prime over u prime means I'm going to take the derivative of each term inside the parentheses. So x derivative becomes 1, 4 goes to 0, e to the negative 3x, that's a special rule, which is e to the u. So e to the negative 3x becomes e to the negative 3x, over here, sorry, e to the negative 3x times negative 3. So everything in the numerator constitutes the derivative of this u prime portion of natural log, divided by the u value. So u value is everything inside the parentheses unchanged, so that goes here. So we have our derivative. I clean this up a little bit. I push the negative 3 in front of the e. And now we have a slope formula, which we can evaluate further by plugging in 0. So replace every x we see with 0. So e to the 0 is going to be 1, so 1 times negative 3 is negative 3. E to the 0 here, that's also 1 as well, so we get 1 minus 3, which is negative 2, 4 plus 1, which is 5. All right, 14. We want to find the derivative. We need to recognize these as two separate expressions. We have to go through the product rule. These are two terms being multiplied together. So I'm going to let x squared be our f. I'll let the g function be sine of 2x. So x squared becomes 2x. We keep the g function. F is the original x squared. Now sine of 2x becomes cosine of 2x times 2. The derivative for sine of u is cosine of u times u prime. And now we have the derivative. We just have to clean this up a little bit. I can push the coefficient 2 in front of the second expression, and then I can factor out the 2x from both terms to make it match our answer choice. Number 15. We have the derivative f prime given on which of the following is the graph decreasing. So this is a first derivative test that we can do, which means that we're going to find the critical points from the numerator and denominator after we rewrite f prime using common denominator. After we pick out the critical points, then we're going to create f prime, the f prime sign line. Then we'll test each interval to see how the graph is behaving in terms of rising and falling. So with f prime, I first identify common denominator, which is x. I balance the numerator for the first term. I pushed it all under one fraction, and now I can look for critical points from the numerator by setting the numerator equal to 0, and the denominator, I'll set that equal to 0 as well. If I set the numerator equal to 0 and solve for x, I get x equals cube root of 2. So that's a critical point that I can place onto my f prime sign line. Denominator is x equals 0. That also goes on the sign line. Now, even though 0 makes the slope undefined, or the derivative undefined, we still want to put that onto our sign line because it still acts as a critical point that helps to separate the intervals of our slope sign line. Now, we have the critical points identified. I'm going to pick points around these critical points and plug into f prime. So if I plug -1 into f prime, I get -1 minus 2, which is negative. Negative over negative is positive. So I know in this region, my graph is increasing. If I plug 1 in, I get 1 minus 2, it's -1. -1 over 1, that's negative. If I plug 2 in, I get 8. 2 cubed minus 2 is 8 minus 2 is positive. Over 2, that's positive over positive, which is positive. So we know our graph is decreasing in this interval from 0 to cube root of 2. Number 16, if the line tangent to the graph at 1, 7 passes through point -2, -2, then f prime of 1 is equal to. So the problem is asking, if we had this graph pass through these, or if there's a tangent line that passes through those 2 points, what is the slope of the curve at x equals 1? Now I drew a potential graph just as a visual. Now we know what the slope of this point is on this curve because they're telling us that it is tangent to the line that goes through those 2 points. So tangent means that it must share the same slope. So if I can figure out the slope of this tangent line, then I know the exact steepness and slope of the curve at that point. So the slope of that tangent line, I just do change in y or change in x, 7 minus -2 divided by 1 minus -2. That gives me a slope of 3. So the tangent line has a slope of 3. So the slope of this graph at x equals 1 must also be 3.